Odometer, right. This is basically an odometer. I represent so I have the two-adic integers, but this is really the limit, the inverse limit of the integers divided by the finite group, integers divided by cyclic, by the integers mod 2 to the n. And this is not just a group, but it's also a ring in which you can multiply elements here. Each of these is a ring, and that's minus 1/3. At any rate, the next expression will be 1 times 3, 1 times 2, etc. So at any rate, there is some expansion, epsilon n 2 to the n, some infinite expansion, and things that have such an infinite expansion where the epsilon n's are either 0 or 1, these are called two-adic integers. And now, 1/3 is a two-adic integer, and so 3 is invertible in the ring of two-adic integers. And so just like you can expand two-adic integers in terms of powers of 2, you can also expand such an integer in terms of powers of 2/3. Thus, every two-adic integer can be written as sigma, that's right, delta n, 2/3 to the n. And this makes sense within the two-adic integers. Now, in this, when I write such a two-adic integer in this way, if the integer is what is meant by the shift, I guess, if this were ultimately periodic, that means that the sequence would be ultimately periodic, which means that the sequence would eventually keep repeating itself. But I know because I'm multiplying, because I've chosen, because I'm in this domain, I know that these numbers are not going to repeat themselves. They're always increasing. They're always different numbers. Even though you may think of them as these are natural numbers and these are two-adic numbers, but if these can't repeat themselves, then these can't. If these can't repeat themselves, nor can these. So the question is now, in other words, this operation of the shift operation, we know is a well, I won't go into the same detail, I'll just indicate something about the spirit of the question. But here the question is, and you can think of it as a question about odd two-adic integers, but it also makes sense. Let's take n odd. So here the domain consists of odd integers. Then what we do is we send n to 3n plus 1. And this is going to be an even integer. So I have to divide. I want to stay inside the odd integer, so I divide out by the highest power of 2 that divides 3n plus 1. And then again I get an odd integer. So again, let's say starting with 11 will go into 34, that'll go into 17, 17 will go into 52, that becomes 26, I'm sorry, that becomes 13, 13 goes into 40 divided by 8. This time this goes into 5. 5 goes into 16. That's divided by 5. 16, that goes into 1. Now 1 goes into 1. It returns to 1. 3 times 1 plus 1 is 4. If I divide by 4, so I end up with 1. Now the version that's most familiar of the question is it true that no matter where you're starting by 4, an eighth of the time you'll be dividing by 8, and so on. And you can figure out that on the average, what you're doing is multiplying by 3/4. I mean, if you think of this sequence as if the sequence would be infinite, and the issue is To my mind, that's really the important question. Can there be an infinite orbit here? And now, the hypothesis is that if it's infinite, it'll be equally distributed among the odd two-adic integers. And then you should be able to predict the statistics, which predict that what you're doing on the average is multiplying by 3/4. But then it can't be going up to infinity, because then it's getting smaller eventually. And so that's the formulation I would like to give to the question: is every orbit, can there exist an infinite orbit? Which is the same thing as saying, the same thing as asking, does every orbit eventually come to some cycle? And this, if you check it, you can do various variations on the problem. Well, for example, you can replace this 1 by anything odd, and you still have the same reasoning applies, the same reasoning would apply, and so the hypothesis would be that the orbits won't be infinite. They will always come to some cycle. And again, you can formulate this in terms of expansions. I don't remember exactly how. It's a different kind of expansion to of the two-adic integers, but in any case, this becomes the shift on that expansion, and then again the issue is, are these points, are these rational points going to be generic? Now, we should end here. I have more questions which have the same flavor. Yeah.
Recently, in a Canadian journal, there was a claim that he has solved this question. Proved in the affirmative that every orbit is finite.
Oh, yes?
2 years ago, it was published.
The claim.
The proof was published. In a Canadian journal. Canadian
Thank you.